I need to sit down. Or like this.
If you go on this, here you can see.
Oh, okay. Yeah. Entendi. So, yeah. Oh, I can change.
But then you have to, when Sisi talks, you have to unmute.
Unmute. Okay. Okay. Right. Okay.
You can start. Okay, so Sisi will introduce you.
Can we start? Yes. So, good afternoon, dear participants of WaterTOP. The first speaker of this section is Professor Gianluca Li Puma. He's Professor of Chemical and Environmental Engineering and Director of Environmental Nanocatalysis and Nanoreaction Engineering at Loughborough University. He has a rich writing and research record. Among other editorial activities, Professor Li Puma is editor of Applied Catalysis B Environmental and member of the editorial boards of Chemical Engineering Journal, Chemical Engineering Journal Advances, and other journals of high impact. His today's talk has the title Identification of Removal of Contaminants of Emerging Concern in Water in Micro and Macro Scale Reactors. Professor Li Puma, the floor is yours.
Thank you very much, Sisi, for the kind presentation, and thank you to the organizer and to Rita Lado for inviting me to give this opportunity to present some of my work to you. Hopefully, if we can start some useful discussion or collaboration also, it would be a nice outcome. So today I'm going to talk about how to intensify advanced oxidation processes for the removal of contaminants of emerging concern in water. So, okay. So, first of all, just a short introduction about the work that we carried out at Loughborough. We cannot see the top line. I don't know why this is this. Maybe my otherwise it's okay. Okay, so these are the topics that we are covering in my research: environmental nanocatalysis and heterogeneous photocatalysis, photomicrobial electrosynthesis system and solar fuels, advanced disinfection, advanced water detoxification and reuse, and then process intensification, photoreaction, solar engineering, advanced mathematical modeling. So today I'm going to talk only some of these aspects, not covering all of these. I don't know why it doesn't work.
Excuse me, with the same problem as before, you cannot see in Zoom the whole slide, just only see a part of it. So could you?
Okay.
Will you excuse us for a moment? We have some technical problem. We will continue in 1 minute. Okay.
So, why to go on and off? Why? I need to use those ones. No, I can't. Okay, all right. So that's where we were. So these are the 4 topics that I described, and I will start first with the application of disinfection, water detoxification, reuse. You can see here we are applying different types of advanced oxidation processes for removal of contaminants of emerging concern, such as photocatalytic oxidation, AOPs using UV hydrogen peroxide, photophantom, sulfate, sanitation, reaction mechanism, and also scaling up these processes to pilot scale systems. So you can see here some of the pilot scale that we have applied. My topic is mainly advanced oxidation. So this slide actually was prepared by Rita Lado Ribeiro. So as you know, advanced oxidation process, there is a range of those, include the ozone-based system, photocatalytic system, homogeneous system like photophantom, and also photophantom in heterogeneous phases, photolysis, and so on. But basically all advanced oxidation processes are based on the generation of radical oxidative species, such as hydroxy radicals, peroxy radicals, singlet oxygen, etc., and peroxide species also. So, as you know, water resources are scarce, so we need to preserve water resources, so we need to reuse water primarily. And this is the largest water reuse purification, one of the largest water purification reuse system in the world, which is in Orange County. That process about 133,000 cubic meters of water per day. And this process involve microfiltration, reverse osmosis, and then advanced oxidation, such as UV hydrogen peroxide. So you can see here the reverse osmosis system here, and then the UV, the ultraviolet hydrogen peroxide system for the plant. And this is a schematic how it works. You have first some filtration, microfiltration, then it goes to reverse osmosis here. Then there is acidification before reverse osmosis, and then there is a bypass in case there is too much water going in. Otherwise, you will go to the UV disinfection system, and then the water is reinjected into the aquifer, and the same water that is used for drinking water. So this process here reassure the removal of some of the contaminants of emerging concern using basically reverse osmosis and advanced oxidation such as UV hydrogen peroxide. And this is a picture of the south of Spain. El Ejido in Spain is basically the Europe's largest greenhouse area. As you can see, it's an enormous area. It's just where all the tomato, the salads comes in the winter all over Europe. And in this area here, there is the cities here. All this is greenhouse. And the wastewater treatment plant is this black dot here. And the wastewater contains both contaminants coming from personal care products and also pesticides that are used in the greenhouse for growing the vegetables. So you can see in this figure here some of the compounds that come out at the end of the pipe after secondary wastewater treatment. Then you can see there is a mixture of pharmaceuticals like naxoprene, and also pesticides like urine, for example, or diclofenac. In red are highlighted those compounds that make 90% of the pollution loads in terms of emerging contaminants. And you can see that the highest concentration is caffeine. Caffeine is pretty much in every pharmaceuticals. You have caffeine. Also, people drink a lot of coffee. So caffeine is one is very high. Also, ibuprofen is very high. There's lots of use of ibuprofen and so on. So this is the range of contaminants that we want to remove before reusing water, ideally. So my first project, actually, well, this was back in 2003. The first European project that was funded, it was about the innovation in sustainable production of natural cork stopper. This is where my experience in odorous compounds, let's say, started. After that, I did not proceed much on this area, but this is my very first work, actually, one of the very first. And as you can see, Portugal is the #1 producer of cork in the world. And basically, you take the bark, you cut the bark, then you put the bark in bath, you boil it for about 1 hour in open bath. This is the traditional method. And then you let it rest to soften. And then after that, you can punch the cork and you have the cork for maybe the wine. But the thing is that when you boil this water, the water is reused up to 20 times, 20 batches of boiling. So the water comes out is this color. It basically looks like completely black. You can see high COD, high TOC. And in this project, our main objective was to remove trichloroanisole, because trichloroanisole is what makes wine goes off. Basically, it's this musty smell that we have. So my role in this project was to develop a water treatment system to remove trichloroanisole and other polyphenols that were included in the water. So we carried out first laboratory experiment in small-scale reactor and also in pilot-scale reactors, as you can see here, using ozonation. And you can see here that I'm not describing here the removal of trichloroanisole, which was removed also. We were doing solid phase microextraction to detect this. We had a talk this morning about this. But you can see the effectiveness of different advanced oxidation processes. And basically, UV hydrogen peroxide was working well, and also ozone with the UV was working well also. But we had to develop a system that could be implemented in industry. So at the end, we decided just to put ozonation for removal of these polyphenols. And we know that polyphenols, ozone has a high affinity with polyphenolic compounds. So we developed a technology together with a company, Alvaro Coelho Maus, in Portugal, in Espinho, not too far from Porto, here, where we could basically have an ozonation system within a boiling batch. So the boiling in this innovating system was not done in open vat, was now done in a closed vat under pressure, under slight pressure, to try to extract as much polyphenols we can, as much trichloroanisole we could from the bark. But in this system here, basically we had, this is done hot water. So we have here the water that needs to be treated. The water is pumped into the ozonation system, cold, because the ozonation is more effective under lower temperature. And then the water is treated there. And then after it is treated, it's transferred to one of these 2 tanks here, ready for use for the next batch. So we had basically a process where we could, within one batch lasts about 1 hour. So within 30 minutes, remove the polyphenols extracted by the previous batch and continuously reuse the same water. So this was a technology that was implemented by the company. So that was my first experience on water reuse and removal of contaminants and also removal of odorous compounds. And then, of course, that was done in a simple ozonation system, a bubble column, as we know. So then I started working more in reaction engineering, trying to optimize the ozonation process itself. So we develop different types. We work on different types of photoreactor designs. Here you can see a lot of publication we have produced on this area here. And these are some of the pilot scale systems that we have developed for different types of advanced oxidation processes. But today I'm going to focus more on the oscillatory flow ozonation system, which is not shown in this slide, but is shown in the next slide. Before going to that point, you can see that geosmin and true methyl isoborneol are some odorous compounds, the one that people detect in drinking water a lot. And this type of processes can be removed, some of them by advanced oxidation. Geosmin not, as you can see, geosmin here really doesn't work very well after ozonation. After ozonation, it doesn't really degrade, but true MIP degrades, as you can see here. There is some kind of degradation from the raw water. So we wanted to develop processes to remove contaminants using ozonation in a more efficient way. So the one that we developed is what we call oscillatory baffle reactor. So I'm a reaction engineering person, so chemical engineer, so not an analytical chemist. So this is a patent process, and as you can see in this process here, basically we reduce a bubble column, which is typically a very tall column, to a much shorter reactor, and we introduce some baffles. So as you can see, there are some baffles here, and we introduce also an oscillatory flow system at the bottom that oscillate the liquid between the baffles. So this produces basically an extremely compact ozonation system. In addition to this, you have a full use of ozone. The major cost in ozonation system is the ozone itself. And this way you need very little and you use it all. There is no loss of ozone. And the reactor footprint is actually 10 to 20 times smaller compared to typical ozonation system. And allow also operation in both batch or continuous process. And it is fully scalable. So we can design this reactor larger diameter, smaller diameter, or taller, a bigger volume also. So just to show you the way it works, this is just upside down, but it's a video. Basically, you have a piston here, they oscillate very fast, and that creates very intense mixing here. You have some baffles here, and the baffle is basically a constriction, so the water has to go in and out like this. During this process, it creates intense turbulence across the whole cross-section of the reactor, and this breaks down the bubbles of ozone, makes micro bubbles, and therefore maximize the rate of mass transfer. So, as you can see, we perform some computational fluid dynamics just to simulate the system here. So, as you can see, the liquid during pumping up pushed through the holes here, it goes up, and then when it comes down, it goes the other way around. And this creates very intense mixing. The design of the baffles, of course, is all everything, the technology is all based on the distance of the baffles, the aperture of the baffle, the design of the baffles, and so on. So this is where the know-how, our know-how comes on. And
batch system?
You can work post-batch or in continuous flow. Okay, this is good because the level of turbulence within the system is independent of the flow rate. You just adjust by changing the frequency and the amplitude of the oscillation at the bottom. And you can compare here what happened in a oscillatory flow system with what happened in a typical bubble column with a mixer. As you can see here, there is no homogeneity in turbulence across the cross-section. There is high turbulence near the impeller, but here there is not much turbulence. While in this system here, basically you have a level of turbulence that is uniform, let's say pseudo-uniform across the entire reactor volume.
Because of the baffles.
Because of the baffles and because of the oscillation. Exactly. So that's where we go from a very tall column to a column that is this high. Instead to be 2 meters high, you can reduce to this size, and you can make the system more compact and easy also to implement in companies, for example. And you can see the performance. This is the removal of para-hydroxybenzoic acid, and you can see in the bubble column, basically there is a lot of ozone immediately, even at very low flow rate, a lot of ozone is lost from the top. Not all the ozone is used. So there's a lot of loss of ozone here, and there is no loss of ozone in this one. Only when you go a very high flow rate of ozone, then you start losing some because it's too much, you pump in there too much ozone. In addition to this, the removal of TOC and para-hydroxybenzoic acid compared to the blue or the red is much more efficient in the smaller reactor size. So the other advantage is that because of this limitation of the ozonation system, you can only utilize a certain fraction of ozone, so you cannot go above a certain value of TOC removal. So the removal of this is the TOC in a bubble column is only limited, but in a oscillatory flow system, you can go to several order of magnitude higher compared to the previous case. So we have this system is being patented. So that is what our first example of process intensification in micro scale reactor. But now I'm going to show the opposite, how to intensify the system in a micro scale reactor. So we are going to a micro scale. So for example, if you want to analyze contaminants of emerging concern where you don't have human standards or illicit drugs, for example, that you cannot get the standards, so you have very, very little, then you need to do all your experiments with very small amount. With that small amount, you want to study the kinetics, the intermediate products, identify the breakdown products, and so on. And if you try to do this using a large reactor, it's pretty much impossible because you need too much of the compound. And in addition, the kinetics are very long, it takes 1 hour to get one data. So you want to make this at the micro scale, so you can have a much more rapid system. So our intention at the time, working with our colleague at University of Naples, was to develop a system to detect cocaine and to try to find out what are the degradation products of cocaine in water, in natural water. And these include benzoyl and cocaine. So cocaine naturally transforms itself to benzoyl and cocaine. And then our intention is, there were this news, Italian river full of cocaine. Okay, but it wasn't just the Italian river. Every river in Amsterdam, you have the highest concentration, in River Thames, the second highest in Europe, in Paris, the third, and so on. So the big city, depending on the size of the city, we have a lot of benzoyl and cocaine. So we wanted to find out what are the effectiveness of advanced oxidation for removal of benzoyl and cocaine. So we couldn't have any samples. This is illicit drugs. This is a controlled system. In Italy, you cannot get any. In the UK, we could get 1 milligrams, and that's it. That's all we had. So we had to perform experiments with this. So we developed a photoreactor system that could give us quantitative information using very, very small quantities. And so we came out together with my colleague, Uno Reis. He's also from Portugal, from Aveiro. He now works in the UK, but he is a Portuguese. He did his first degree in the University of Aveiro. So we developed this, what we call it, a microcapillary film photoreactor. That's our first publication in COM in 2015. So it is basically a film where we can pump through a liquid which contains our whatever we want to study, and then we can fully irradiate this using UV or using other system or perform advanced oxidation experiments. So as you can see, you have a very film. This film is very thin. It can be very long. You can make as long as you want. If you want it to like 10 meters, we can make 10 meters. You want it shorter. You have some very small orifices here. The range is between 100 micrometers up to 1 millimeters, even 2 millimeters. And you have a flat surface also, top is flat. So you have in this case, you have 10 little microcapillaries in there. And the advantage of having a flat surface is that when you irradiate with light, there is no bending of the light here. So you go straight through the microcapillary. And also because it's very thin, you basically have almost a uniform irradiation. So there is no gradient across this. Even if you have a high turbidity of the water, you don't see any gradient in absorption of light because it's very, very thin. Okay. So we use this system first to do some experiment using some viruses to remove viruses in dense protein solution, and that was effective, and also to remove dyes or to remove diclofenac, or to remove benzoyl-coganin. As you can see here, the kinetics are very, very fast. You can have basically up to 90% removal with fluid residence time of 1 second, 1.5 seconds. In addition to this, you use very, very little water. You use here 2 mL of water, okay, to do one of these experiments. So 2 mL is, with 100 mL of solution, you can make a lot of data. You can generate a lot of data. And what is the advantage of this? Is that if you can also connect this to analytical system, could be GC or can be LC in this case, LC-MS, connect the two, you can have also online detection of intermediate products, as you do. So how do you change the residence time? You just change the length of the irradiated area, okay? So you typically, you take this film, you wrap around the UV lamp, like this, like a coil, and then you change the length of the irradiated area, you change the residence time, basically. So very easily you can get some data. So we start working with Susan Richardson, University of South Carolina, who is well known across the world for LC-MS, time of flight, for especially for detection of microcontaminants in water, drinking water, and also water for recreative purposes, like in swimming pool. So we sent the sample to them. Of course, we did some solid phase extraction, and then we set the solid phase extraction. And obviously, they were doing the GC, the LC-MS. We were doing the kinetics. As you can see, how the kinetics can change if you use ultra-pure water or if you use synthetic wastewater. There is a decrease of the effectiveness of UV hydrogen peroxide in this case, but it is still effective even in synthetic wastewater. So once we send the sample there, then we can do some LC-MS, and you can see here the evolution of the breakdown products. This is with just UV. So you can go when you have, this is the pure water, this is after 40% conversion of benzoyl-coganin, and the other one is after 85%. So you can see, you can follow what happened to the reaction. Basically, if you can connect this online, you can actually follow real time. In this case, it was not real time. It was like we had to send the sample to the US and then do the analysis after. This is a CMS orbit trap. And then we did the same experiment with UV hydrogen peroxide, and of course the product's profile changes depending if you use UV alone or UV hydrogen peroxide. So you can find out if there are any toxic compounds. We also did some toxicity study on the samples that we get. So at the same time, you very little. For toxicity study, you need to have a lot more water. You need to have about 1 liter of water going through the system before you can do those kind of studies. But for the purpose of finding out the breakdown products, you only need a few mil. So you can see the various compounds that were detected during this type of analysis. This one was detected, another one here, and another one here, and another one here. So basically, we were able then to map the reaction mechanism of reaction of benzoyl-coganin with, in this case, hydroxy radicals produced by UV hydrogen peroxide process. The same technique can be applied also for removal of odorous compounds in drinking water. We also start focusing on the photodegradation of pharmaceuticals, such as antivirals, such as acyclovir, antiretroviral like zidovudine and stavudine, and also biocidal antifungal agent, as you can see here, this one here. And what our objective of this work was, one, finding the intermediate products, but the other objective was to find out the second order reaction constant of reaction of pharmaceuticals with hydroxy radicals, which in some cases are known, in some cases are not known, especially for new compounds. We don't know them. using a microcapillary system, we can determine this. So in order to determine the second order reaction rate constant, which is basically the reaction of, in this case, a cyclovir, the hydroxy radical to form intermediate products. So it's the first step of the reaction, let's say. We need to have a reaction mechanism. So working with our colleagues in the University of Naples, we developed a very simple, in this case, implicit reaction mechanism. And then by assuming that the flow through the system is kind of plug flow, which actually is not, because it's laminar flow, okay? We were able then to determine this rate constant. So in addition, our colleague in University of South Carolina were determining the breakdown products of acyclovir also. Some were known in literature, some are new breakdown products that we determined here. And by fitting the experimental results here under different conditions, different light intensity, different initial concentration of oxygen and so on, we then be able to determine the second order rate constant of acyclovir. Okay, in this case, you can see the value here and the range of validity here. So we did this for acyclovir, and we did this also for zidovudine, stavudine, also the same, the data there. And the same for the other three compounds, isaxazole, isothiazolone, and benzyl isothiazolone. And again, doing the same technique, we can do this. However, that was not the end of the story. Because one PhD student came to work with me, he actually specialized in computational fluid dynamics. So we asked the question, are these data real? You know, is it real to assume a plug flow through this type of reactor, which actually is working under laminar flow conditions? Well, okay, let's analyze this problem. So we performed some tracing experiment using a tracer, and we basically found out that the flow was not plug flow, because if it was plug flow, it should have a sharp. We were injecting the tracer, we should have a sharp step here, but it was pretty close to plug flow. And it is although the flow is laminar, because the Reynolds number is very, very small. Chemical engineer understand me when I talk about Reynolds number. So it's laminar, but because there is the wall effect, is very close, this wall, the diffusion effect across the wall, it effectively behaves close to plug flow, but it is not plug flow, but it is also not, but it's pretty close, let's say. But there was a second problem here that we had in this system, is that this was not a straight reactor, it was a coil reactor. So because if it was a straight reactor, we should have followed this line, but the data were not following a straight reactor line, they were following this line here. So the question was then, why is that happening? Well, this is happening because we start realizing that in addition to axial mixing, there was also transversal mixing through the reactor due to the fact that the reactor was coiled. So you have a change in momentum of the fluid because of this, and this creates secondary flow, secondary mix in the reactor, and therefore the assumption of plug flow is not a correct assumption. So we start doing this work. So we introduce.
It's like running in a race.
Yeah, it's rotating. So you have the.
That it's outside. You need to do more. Need to run faster.
Well, it is not about the speed of the light. It's if you go straight, it's to do with the centripetal force to the liquid. The liquid is going round, so because it's round, actually there is a force onto the liquid that is also want to mix in this direction. So we did this. So we went back to fluid mechanics books, and we started learning about the D number. So from the D numbers is basically equal to the Reynolds number, multiply the diameter of the tube. So this is the diameter of the microcapillary and the radius in which you are wrapping it, okay? So at the denominator. So the smaller the radius, the stronger this force this centrifugal force. So that means that because we are wrapping this in a very small radius of the lamp, which is only a few centimeters, we have a strong force generating this. What does the force do? The force creates lateral mixing, create this kind of mixing within the coil, which in a way is a good thing because it mixes the liquid as it goes through rather than going straight through. Okay, and therefore we determine under which condition this kind of force becomes predominant. So we produce this graph so we can say that when this the D number and the Smith number is higher than 100, then you have this lateral mixing becomes important. And this is also important because in terms of reactor design, you want to introduce curvature if you want to mix things in a lateral direction, not in the direction of the main flow, just coil the tube and that will produce that kind of mixing. So it also means that the prediction that we did in our earlier paper, assuming plug flow model, were not correct. So we redid the calculation again using computational fluid dynamics, introducing this effect to the tube, and we recalculated the second order rate constant for our compounds, like you can see here. And the errors, there were some errors that were going from 4% here, 10%, 16%, even up to 37% errors on our initial calculations. So we adjusted that and we published this recently, this data. The other implication that you have when you coil the reactor is related to the electrical energy per order. Because of the mixing actually what does? It brings reactant away from the light, close to the light, because of this lateral mix. So in this case, if you have a system that has a dim times width, which is quite large, you can actually reduce the amount of energy that you need to remove one order of magnitude of concentration of contaminants. So there is also an advantage in terms of reactor design. It's not easy to see in real terms because to go into this region, you need to have a very, very narrow, maybe a high flow rate, a very cold system. But at least from the analytical point of view or mathematical point of view, we can predict this happening. So thank you very much for this. This is Rodrigo that did the computation fluid dynamics. This is Danila and Mariana did the experiment using the microcapillary flow. This is the group that worked. Actually, I don't have a picture of the group working on the cork because that was in 2003. But this is a picture at University of Patras. As you can see, some of you are from Patras. And this is the group of Professor Susan Richardson. And thank you again. If you have any questions, I'll be glad to answer them. Thank you.
Professor Li Puma. Professor Li Puma, thank you for your very, very interesting presentation.
More engineering than analytical, I guess.
Okay.
Question now. Yes.
Can it be applied to point of view systems that can treat water, or is very complicated? The coil is simple, but another system can be.
Yeah. Actually, yeah, it's a relevant question. It's a question I get all the time because you are actually treated a very little amount of water going through, only a few mil in this system. This kind of system you can use first for detection of certain breakdown products, maybe. In terms of scaling up, I need to put it on, otherwise they're gonna hear. Okay. In terms of scaling up, I mean, there are different strategies. You can use instead to coil, you can use also UV LED Yeah, so you can use UV LED, so you can have a system that is kind of packed with this going through in one direction like this, and the other direction, so like this one with UV LED in the middle. So you can make a quite compact reactor there. So, but in terms of scaling up, this is treatment of a glass of water that you're going to drink, or only for a few liters per person per day. Yes, you can do that, but not for treating.
No, I'm talking about quantum.
Yeah, point of use is scalable. Yes. Yeah.
Yeah, and actually, I also think that when it comes to UV energies, there could be more potential for this kind of technology, because it provides more flexibility compared to low pressure lamps, and you can have system design, custom design.
It's true. The only problem with the UV LED is that at the moment the UV at 254 nanometers is quite expensive to produce with UV.
Yeah.
The efficiency also very low compared to, if you're in the visible light, that's okay. But the same technique can be used also with other advanced oxidation processes. Persulfate, for example, that doesn't need UVC, you can work with UVA. Phantom, photophantom, so other type of system. We have not worked on this but
yeah,
the same can be done.
I'm just curious about medium pressure lamps instead.
Okay, the problem with medium pressure lamp, which I did work in my early studies, actually, if you see some of the picture, let me go through this one very quickly. Some of the reactors I did not describe in detail. This is probably the best example. That's me when I was a student. Was my master degree. This is the University of Bath. We are talking in 2001. No, sorry, 1991 or 92 at that time. 92. And this is probably the first reactor using medium pressure mercury lamp, the first pilot scale reactor, one of the first in Europe, because it was 200 liters, it was quite a beast. And you had 9 kilowatts of power inside, 9 kilowatts in 200 liters, the water got hot. So we had to have a cooling system. It was quite a nicely engineered system, but far too much power there. So we developed a smaller one using low pressure mercury lamp. The problem of using medium pressure mercury lamp and this microcapillary is that the heat is too much. So the microcapillary will melt through that.
Right.
So that's why we prefer to use low pressure mercury lamp or even UV LED at certain distance.
UV LEDs could be interesting perhaps in 5 to 10 years.
Yeah. This is our first prototype of oscillatory flow system, very small. Okay. This was like this reactor, but then when I showed the ozonation was a 12-inch diameter tube, about this big. But our expertise is to scaling up whatever process to remove contaminants and emerging contaminants, including also other compounds in drinking water. And as I said, in drinking water, you only need to produce 3 liters per person per day. You don't need to produce cubic meters of water per families. There's no need to have super clean water for shower or for washing your hands.
Yes, I would like to ask you. Okay, yes. I would like to ask you, which method did you use to measure the second order reaction rates with hydroxy radicals?
Okay, we perform a study with both competition kinetics and reaction mechanism. So what I show you here is using a reaction mechanism. So we are not using competition kinetics, but also we compare our results with competition kinetics. There was some difference, maybe 20–30% difference, but the competition kinetics method also has some intrinsic error. So if we have an error in the system we were using, was our mechanism. Maybe our mechanism was not as detailed as it could be. Okay, but that can be changed. You know, you only need a more detailed mechanism. At some point, you need to decide how many elementary steps you're going to include in your reaction mechanism. Okay, with computational fluid dynamics, it's easy to do that because you can increase the number of steps. It doesn't change much. To the computational time, yes, it depends also on the number of steps, but you know, we are still talking of several hours of computation, several days. So one day more, one day less doesn't make much difference. You can increase the number of steps. Yeah.
There is a question by Tri, as I see here, in chat. He says, great presentation, thank you. How do you approach electric energy per order from lab scale to real scale? Can you have a good prediction of EEO in real scale?
Good question, very good question. In this presentation, we only predicted the electrical energy per order for microcapillary system. So in this slide here. But we have the same slide, the same figure like this, for example, for a scaled up photophantom raceway reactor. So I will direct the person that asked the questions to our publication recently I think it was in applied catalysis of water research together with a group of José Antonio Pérez in University of Almería, in which actually we use computational fluid dynamics to model raceway reactors. In that case, we had the scale-up reactor systems. Right now, I know I was there actually last month. We were working on computational fluid dynamics of a full-scale raceway reactor that was about 100 meters long and going around like this. So we are working right now on the computational fluid dynamics of that. And we calculate also the electrical energy for that kind of large-scale systems.
Can you say a few things about this fountain reactor?
The
fountain reactor.
Ah, the fountain reactor.
Very interesting.
Yeah. Now, the fountain reactor is a reactor that, let me go, I'll show you the picture of the fountain. It's a reactor that I developed when I was at Hong Kong University of Science and Technology. It's one of my, actually, some of my first publications were done on the fountain reactor. We're talking 99, 2001, in industrial engineering chemistry research. So the idea was basically to have a lagoon with fountains, with lots of these fountains, which obviously have the multiple advantages of having the fountain. You have oxygenation of the water, but also in this case here, we were adding a photocatalyst, titanium dioxide. So our idea was to use a lot of photocatalysts, so to have a very high optical thickness, but because you have a very thin film here, you have a pretty much high absorption of light, of radiation. So we developed this fountain reactor here in the laboratory. This was about something like that big, it was maybe 1.5 meters in diameter. We performed the modeling also this, so you can see some of the papers doing modeling of the fountain reactor and also scale up. If we want to treat a certain volume of water, how many fountains do we need? And we did this work for the removal of pesticides, isoproteron, simazine, and propazine, including a cost analysis also. So we've done also the scale up to this, and the reader can see my very early publication in beginning of 2000. We still working on the fountain.
From all advanced oxidation processes,
Yes. From all advanced oxidation processes, which one do you think that has all the necessary characteristics to be effective and at the same time suitable for the real use for water treatment?
Okay, we need to distinguish, of course, if it is wastewater or if it's drinking water.
Yeah.
Okay. So for wastewater, you can see that already UV hydrogen peroxide has been implemented in the Orange County in the water reuse purification system. So UV hydrogen peroxide is used. all UV is also used for UV disinfection, of course. And ozonation is also another advanced oxidation that is used for wastewater. For drinking water, ozonation, the problem with ozonation is the formation of bromates if you have bromine. So it can be an issue there. But for drinking water, I think Switzerland is using, I don't think it's for drinking, it's still for wastewater. Switzerland is using activated carbon, GAC, and ozone. But for drinking water, I think the UV hydrogen peroxide can, you need to have a treatment that is able to remove any hazardous compounds if these are formed. Persulfate, no, because the salinity of the water increases if you use persulfate. If you use phenton also, no. But yeah, UV or also ozone, but ozone you need to be careful also because the risk smelling ozone can be one. Photocatalysis can be one. I think if you can immobilize the photocatalyst. But whatever you do, I believe that one technology alone is not able to do the job. So you need to combine this with microfiltration, reverse osmosis, UV, maybe advanced oxidation for drinking water, for removal of pharmaceuticals or pesticide residues that can be in the water. But I think it's possible to do this. If you work with a company like Philips, Philips is listening, is willing to develop a water purifier, so such as we have a washing machine, dishwasher, we can also have a water purifier, especially considering how much plastic we use right now when we drink bottled water. So that from the environmental point of view, I think it makes sense to develop a water purifier now rather than buying plastic bottled water.
Okay, so thank you very much again for your very interesting lecture.